Okay, thank you very much, Subodh, and let me thank the organizers of this very nice conference for inviting me to talk and to give this this last presentation of this very interesting series. So you've heard already about primordial black holes several times by Marco just now, and also in this talk by Teruaki Suyama. And the question I would like to ask today is that well, we know that for primordial black holes to form, we need large primordial overdensities. So if this is the case, what would we learn about the physics of the early universe if primordial black holes were observed? Of course, as I will also show, even if primordial black holes are not observed, we also learn something about the early universe physics because it allows us to put some constraints and rule out some possible scenarios. But in both cases, we will learn something. So the idea is that there are two main answers to that question. The first one is fairly well known, and the second one is maybe less often advertised. So the first answer is, well, if we observe primordial black holes, then we have a way to probe the end of inflation. So this is a point that Marco has just made a few minutes ago, so I will be quick. But if you consider this possible potential for inflation, where inflation proceeds as the inflaton rolls down this plateau region, which we know is in good agreement with the data, then you have some sort of a funny feature, inflection point-like feature that I will comment on in a minute. And then the potential becomes too steep for inflation to proceed, so inflation stops. And we know that the scales which emerge from the Hubble radius towards the end of inflation are typically very small. They have a length today which is of the order of 1 meter if inflation takes place at 10 to the 16 GeV, otherwise they might be larger. But in all cases, this corresponds to scales which are way too small to be probed by cosmic microwave background experiments, for instance, or even other cosmological surveys. Instead, when you look at the CMB, the scales that you actually probe are produced at a much earlier time during inflation, 50 or 60 EFOLs before the end of inflation. So there is a window in the potential which is roughly 7 EFOLs long, as Marco pointed out. So the part of the potential that you actually probe in the CMB is this region on the plateau. In between, there is little that we can say about the shape of the inflationary potential. However, if it happens that you have a flat region of the potential again close to the end of inflation, which leads to the production of large fluctuations, which later collapse into primordial black holes, then you might have a way to say something about those missing scales and therefore this missing part of your inflationary potential. So that's why primordial black holes could be an important probe to better understand the physics of inflation or of what happens immediately after inflation. So the idea is that, primordial curvature fluctuations, zeta, which are produced during inflation, when they re-enter the Hubble radius after inflation, they give rise to an overdensity, so to a density contrast, delta rho over rho, which is of the same order of zeta. And if this density contrast exceeds a certain critical value, which we call zeta c, then they collapse and form a primordial black holes. So this is, of course, a very simple and rough criterion, and Teruaki has very well explained that one should, in fact, consider more complicated criteria. But for what I want to discuss, it is okay. Also, the value of zeta c is often debated, and there are many works which try to assess it in different configurations and density profile and so on. But for what I want to discuss, I can take a value which is of order 1. I could take 0.1. It wouldn't change the conclusion. So let's just take this to be of order 1. So if you have a certain model for the early universe, say a certain potential for inflation, if you want to predict the abundance of black holes, what you need to do is have a way to compute the distribution function of the curvature fluctuation zeta, so this P of zeta, and then integrate it above the formation threshold zeta c, in order to derive the abundance, so the probability by which a certain Hubble patch will collapse and form a black hole. So this has been advertised before, but just a brief reminder of why primordial black holes might be interesting in cosmology in general. So they could constitute a substantial fraction of the dark matter. There are tight constraints at the moment, but there are still a few windows in terms of mass which are open for having dark matter being made of primordial black holes. Something which is becoming maybe more and more discussed at the moment is the fact that primordial black holes might provide progenitors for some of the LIGO VIRGO events. And you might have seen yesterday that there was a public announcement by the LIGO VIRGO collaboration of a very, very interesting black hole merger event with two black holes with very large masses, one with the mass of 85 solar mass and the other one 66 solar mass. And because those two masses fall in a mass gap where astrophysical objects could hardly give rise to such massive black holes, even themselves in the paper they say that, well, since the binary components are unlikely those to have formed directly from stellar collapse, it is possible that they have a primordial origins. So of course, it's too risky to say something at this stage, but if new events like this are detected and if the measurements get improved, maybe this will also point towards primordial black holes. Now, even if primordial black holes do not constitute all of the dark matter, they could still be of some interest. For instance, they could provide seeds for cosmological structure formation, and also they might explain the existence of the supermassive black holes that we observe in the center of the galaxies, in galactic nuclei. There are other hints in favor of primordial black holes' existence. Here I refer to this nice paper by Juan Garcia Bellido and Sébastien Claes, where there are other things which are discussed. Okay, but the point that I would like to make today is that if primordial black holes are detected or constrained, then we will also learn something about quantum diffusion during inflation. So during inflation, the dynamics is driven by two main effects. The first one is the classical drift of the field down its potential. And the second one is stochastic diffusion, which is related to the quantum nature of the field. And as a matter of fact, cosmological observations that we have nowadays, so for instance, CMB measurements, mainly probe the first aspect of the dynamics, so the classical drift, but we know little about quantum diffusion. So what I will try to convince you of is that, well, primordial black holes would give you a way to probe that aspect of the scenario as well. And the question this raises is the following. So we know that primordial black holes need large fluctuations to form. But if large fluctuations are produced during inflation, well, they might as well back-react on the expansion dynamics. Now, the problem is that during inflation, cosmological perturbations have a quantum mechanical nature. So this back-reaction, if it happens, would be a sort of a quantum back-reaction phenomenon. However, the state in which cosmological perturbations are placed, the quantum state, has very specific features which allow one to have an effective theory, which is a stochastic theory that I will explain, that incorporates their back reaction and which makes this problem much easier to address. So this is just a brief reminder of Jerome Martin's talk this morning, where he explained that during inflation, cosmological perturbations are placed in what we call a two-mode squeezed state, which is a Gaussian state. That this state has a number of interesting properties. For instance, the evolution equation of the Wigner function of the state is just a classical evolution equation. So it's just given by the Poisson bracket between W and the Hamiltonian. And that if you want to compute the expectation value of any quantum operator, then this can be done by integrating this Wigner function, which is a positive function, against what we call the Weyl transform of O. And then in the large squeezing limit, so when you wait that perturbation have spent some time outside the Hubble radius, this Weyl transform is nothing but the operator function itself, so you lose any subtlety related to operator ordering, for instance. And this explains why things behave in a classical way. So this equation here implies that you can reproduce and understand the dynamics of the quantum states outside the Hubble radius with a classical stochastic theory, where the distribution function is just given by this Wigner function. Of course, there are some subtleties, so this would apply only for what we call proper operators. And Jerome has explained that there are some other classes of operators for which this will not be true, but for what I want to discuss, I only focus on such proper operators, and I can really use a classical stochastic picture. So this classical stochastic picture is called stochastic inflation, and can be derived in the following way. So during inflation, the Hubble radius is almost a constant, and fluctuations cross out the Hubble radius. So they start from being set in the vacuum and Minkowski spacetime, which we call the Bunch-Davies vacuum, and then particle production occurs on super-Hubble scales. So now if you define your background geometry, or if you define if you coarse grain your fields outside the Hubble radius, you only keep wavelengths outside the Hubble radius. Then because of this simple picture, you see that quantum fluctuations will source the coarse grain theory, just because at every time you have new quantum fluctuations which cross out the Hubble radius and join the coarse grain sector. So this is really quantum back reaction at play. And the way that you can model this is as follows. So if you consider any field phi, here I take the inflaton field, but it could be any field at play during inflation. If you Fourier expand it on Fourier modes, and if you only keep those modes k, which are smaller than the Hubble radius, so you coarse grain your theory, you only keep the super-Hubble modes. And if you ask the question, what's the dynamics of this coarse grain field, this is what you get. So in this expression, you see you have two places where you have quantities which depend on time. So when you differentiate phi with respect to time, you have two terms on the right-hand side. The first term is the regular term, is the usual term, is the term that you get by differentiating the mode function. And because you look at super-Hubble scales, you can neglect gradients. So it means that those mode functions evolve with the same equation of motion as the background. And you get this first term, which is just a conventional a Stirl term where phi is driven by the slope of its potential, the gradient of its potential. But because the lower bound of the integral is also time dependent, you get another term which just mimics the fact that again at every time you have new modes popping up from sub-Hubble scales and joining the coarse grain sector, and this gives rise to this second term, which can be interpreted as a stochastic term. So you have h over 2 pi times psi, where psi is just a Gaussian noise. And this equation here can be seen as a Langevin equation, right? So as a stochastic equation. So the dynamics of phi becomes stochastic. So this is just a very brief summary of stochastic inflation. This is of course a schematic derivation of this Langevin equation. You can derive it in a more formal and rigorous way, but this is just to give you some insight into where it comes from. Now, there is an argument which is often made in the literature, and that I will try to I will try to explain that it does not apply here, but because it's so common, let me explain what it is. And this argument is the fact that if you take this new term, the h over 2 pi psi, and if you compare it with the amplitude of the classical drift over one e-folding number, then you get a ratio which is of the same order as the predicted amplitude for zeta. And then the argument goes, well, we know zeta should be small, just for perturbation theory to apply anyway. It means this ratio needs to be small, so stochastic effects are small, and therefore they can be neglected. So the reason why this does not really apply here is twofold. The first one is, well, in order to compare those two terms, because they scale in a different way with time, you need to specify a time scale. Here you take one e-folding number, which is indeed the relevant time scale for the expansion dynamics, but this is not the relevant time scale for what we want to discuss here. So there is a first choice here. And the second reason, which is maybe easier to understand, is the fact that in order to derive this formula, so in order to say, well, this ratio is the same thing as the typical amplitude of zeta, you need to use the classical formulas, which neglect stochastic corrections, to compute zeta in the first place. Therefore, if stochastic effects dominate, this formula is wrong just because zeta is not given by this ratio anymore. And as I will show explicitly, you can find very easily situations in which stochastic effects provide a dominant contribution to the field dynamics, but yet the typical zetas are small and the power spectrum is small and everything is fine to that respect. So how do we compute? So let me remind you that what we want to do is to compute the distribution function of curvature fluctuations in order to compute primordial black holes abundances. So how do we get from stochastic inflation to zeta? And this can be done using the Delta-Lorentz formalism that was introduced by David Wans in the first talk of this conference. But because it was the first talk, let me maybe just remind you quickly what it is about. So it is a result in cosmological perturbation theory, which simply states that on large distances, if you look at the fluctuation in the amount of expansion between an initial slice, which is spatially flat, and a final slice, which has uniform energy density, this fluctuation in the number of e-folds is nothing but the curvature fluctuation itself. So why is this result useful for us? It's because, well, with stochastic inflation, we have a way to compute the fluctuation in the number of e-folds, right? So starting from a fixed initial field value, if we simulate several realizations of the Langevin equation, then we get different times for inflation to end, and therefore we are able to compute a distribution function for the duration of inflation. So if you subtract the mean value for that from that distribution function, it's because of the delta n result, it directly gives you the distribution of the curvature fluctuation itself, which is what you want to compute. So the way it goes in practice is the following. This is a little bit formal, but just to give you the main idea. So starting from this Langevin equation for the field, you can get a Fokker-Planck equation, which tells you how the distribution function of the field value evolves as a function of time. So formally, you can write it as dp over dn is some differential operator that we call the Fokker-Planck operator applied on p. And then what we can show is that if you now think of the distribution function for the duration of inflation, so this calligraphic p, so this is an object which is very different from the straight p. This is the distribution, this is the probability to realize any folds starting from a certain fixed initial value. But although these two objects are very different a priori, they obey very similar equations of motion. The only difference is that now you have the adjoint of the Fokker-Planck operator on the right-hand side. So the computational program is the following. You first solve this first passage time problem. So you have to solve this adjoint Fokker-Planck equation, basically. From that, you obtain the distribution function of the curvature of the number of e-folds, which you identify as the distribution function of the curvature perturbation. You integrate this distribution function above the formation threshold in order to extract the abundance of primordial black holes. So in the last 10 minutes that I have, I will apply this program on a simple model, which is a toy model, so not a realistic potential, but it will allow me to highlight some of the main features and conclusions that will be more generic than just this toy model. So here I'm considering the case where inflation proceeds on a single field potential. So the CMB scales emerge when the potential has a nice plateau shape. But then at smaller field values, before inflation ends, I imagine that there is a region of the potential where V, the potential function, is exactly flat. So the width of this flat region, which we call the quantum well, is noted delta phi well. And the height of the potential V, small v, where small v is just the potential energy rescaled by the Planck mass to the fourth, is called V naught. So the question is, if I start from a certain phi start value within that well, what is the distribution function of the number of e-folds that is being realized? And so this can be computed analytically in an exact way. So this was done in this paper by Chris Patterson, Kushiara Sadulay, David Wands, and myself. And this is what you obtain in a log-log scale. So you might say, well, there is no numbers on the axis. And the reason why there are no numbers is because you can show that this profile is in fact universal. Once you have computed this mu squared parameter, which is really the crucial parameter here, and which is the ratio between the square of the width of your flat region divided by its height. So once you know this parameter, the quantity n over mu squared has a universal profile, which is given by this funny shape here. There is also, of course, some dependence on your initial conditions, so where you start in the quantum well exactly, which is given by this parameter x, which varies between 0 and 1 as you go across the flat region. So there are three main parts in this distribution function. First of all, you have a quick rise. You reach a maximum when n is of the order of mu squared, of x squared mu squared. Then there is a power law decay, which is a very, very mild decay. So the distribution only decays as 1 over n to the 3/2, 1 over n to the 3/2. And then at some later point, when n becomes larger than mu squared, there is an exponential decay instead, so a much quicker fall off of the distribution. So these three regions have implications that I will discuss in a minute. The first thing I would like to point out is, because the typical value, you see that the most likely value is of the order of mu squared. When you compute the mean number of e-folds, you find that it is also of the order of mu squared. So this mu squared parameter is really some way to quantify how much time you spend in this region of the potential dominated by stochastic effects. And something you can immediately do is just integrate this distribution above the formation threshold in order to extract the primordial black hole abundance. And what you get is the following. So here is the mass fraction as a function of this mu squared parameter, which I said is the most important one. There is also a mild dependence on x. So the blue line corresponds to x equals 1. The green line is x is 10 to the minus 4. So you see that this dependence on x is in fact not so relevant. And as you can see, the dependence on mu squared, on the other hand, is very important. So when mu squared is much smaller than 1, the mass fraction is absolutely tiny. So you get very, very few black holes. While if mu squared is larger than 1, you get way too many black holes. So the conclusion is rather clear. You need mu squared to be less than 1. Otherwise, you have an overproduction problem of those primordial black holes. And this result does not depend much on the precise value for the critical threshold that I've chosen, as I was saying before. So the fact that mu should be much less than 1 is, again, another way to say it is that you should spend, on average, less than 1 Folding number in the flat regions of the potential. You might want to ask, well, what do you mean flat region? So here, flat region is obvious. I've just taken a flat potential, so flat is flat. But if I look at a more complicated or more realistic potential, how can I find that there are regions? What is the criterion for having regions dominated by stochastic effects? So what is the criterion for having flat regions? And in fact, you can show that there is a simple criterion, which is given by this formula here, which is v prime squared much less than v squared v double prime. So remember that v is the potential height divided by the Planck mass to the power 4. So because the left-hand side is proportional to v squared and the right-hand side is proportional to v cubed, it means that because v needs to be very, very small, most of the time this inequality is not satisfied, and therefore you're dominated by classical drift, so you have very little stochastic effects. On the other hand, if you have a point in your potential when the derivative becomes very small, for instance, if you have an inflection point, flat inflection point, where the derivative becomes even 0, so flat point in your potential, then this inequality will be satisfied. And in practice, what you can do is just measure the width, the field width of the region where this inequality holds. So you have your delta phi well, you square it, you divide it by the height of the potential at that point, and you get an effective mu squared parameter. And then you compare this effective mu squared with 1. If it's less than 1, you're fine. If it's larger than 1, then the potential is immediately ruled out because you overproduce primordial black holes. As I was saying before, even the fact that we do not observe the universe to be filled with black holes now is already a way to exclude some scenarios for the early universe, and in particular, potentials that would have flat points where close to which the effective mu squared parameter is larger than 1. Something that I just mentioned but do not really spend time on is, you might ask what happens if phi squared goes to infinity. In this case, you see the slope here goes as 1 over n to the 3/2 until n equals infinity. And then if you want to compute the mean folding number, for instance, you get an infinite value. So this is a phenomenon that we call infinite inflation, and there are ways to renormalize this away, but I think I don't have time to really explain what we do here. Something else that I would like to stress on this distribution is that it's completely non-Gaussian. Okay, so in particular, the tails, which in the Gaussian case are just exponential minus something n squared, here are just decaying exponentials, which is very far from being Gaussian. So you have a much less suppression of large fluctuations than what you would deduce from the Gaussian result. And this is in fact completely generic. So you might fear that I obtained this because I looked at a very unrealistic and funny case where the potential is exactly flat. But in fact, in this paper by Jose Maria Esquiaga, Juan Garcia Bellido, and myself, we were able to show that these exponential tails arise all the time, okay? Even if stochastic effects are subdominant, in fact. So there is a way that you can always expand the distribution function in terms of decaying exponentials. So with this exponential minus lambda n times n, and then whether or not you overproduce primordial black holes pretty much depends on the value of lambda n. So in the case of a purely flat potential, the one that I've just shown, the lambda n is given by 1 over mu squared. So again, if mu squared is very large, the lambdas are small, which means you have very little suppression on the tails and you overproduce primordial black holes. mu squared is very small, the lambdas are large, and you avoid that problem. Then you might ask, what happens if I add a small slope in my potential, a small alpha slope, and then you find that the whole spectrum of eigenvalues lambda is shifted by a constant value, which is alpha squared over V naught. Remember that V naught is a very, very small number. So this means that unless alpha is also very, very tiny, then you get a huge suppression of primordial black holes again. But then you might say, okay, let's look at a case where you have a flat inflection point. So close to the flat inflection point, you can Taylor expand your potential with this 1 plus alpha phi cubed. And then what you find is that all the lambdas are very small because they involve V naught, which is smaller than alpha, which is also small to the power of 1 over 3. So in that case, you necessarily overproduce primordial black holes. So this is just a plot of the distribution function that you get in that case, computed numerically. The full lines or the full result, the dotted lines or the Gaussian approximation. So you see that close to the maximum of the distribution, the Gaussian approximation is great, but on the tail it fails completely. And in particular, this shows that if you have an inflection point, well, you overproduce primordial black holes, with one caveat though, which is that here we have assumed that the Searle approximation is valid in order to perform the calculations. Of course, if Searle is violated, so if, for instance, as you approach your flat inflection point, you move away from the Searle attractor and enter a regime that, that is called ultra-Searle, then in that case, this calculation does not apply and you might avoid the overproduction problem, but at least we can make the statement that potentials with inflection points where the Searle is not violated will always overproduce primordial black holes, and all these models can therefore be rolled out on this basis. So it's a rather strong result. So let me just conclude here and say again the main results that I've stated. So primordial black holes can be seeded by large density perturbations that form during inflation. When this happens, quantum diffusion, which is the back reaction of the quantum fluctuations as they cross out the Hubble radius, plays an important role. I've shown you a very simple criterion to identify the regions of your potential where stochastic diffusion plays an important role, and it's given by this simple formula with just the potential and the derivative of the potential. I've told you that if you have a region where stochastic effects dominate, so where this criterion is satisfied, then you find that the system should spend less than one folding number on average, otherwise you overproduce primordial black holes. Because of that, for instance, you're able to rule out flat inflection point potentials, at least if they do not violate Searle. Otherwise, the question still remains open. What is the abundance of primordial black holes in that case? And we are working on that. I know that several groups are also working on that, so I think it's something that we'll find an answer pretty soon. Something else I said is that even in regimes where you have a domination by the classical drift, you still have these non-Gaussian tails. So for instance, even at CMB scales in principle, of course, the neighborhood of the maximum of the distribution is Gaussian to a very good approximation. So this explains why we see Gaussian statistics in the CMB, because the fluctuations we see are the most likely fluctuations, so the ones which form from the maximum of the distribution mostly. But the tails are still non-Gaussian and exponential. So it means that, for instance, if you looked at objects which are rare, such as primordial black holes, but also ultra-compact mini-halos or other things like that, then you will really probe these non-Gaussian tails. And it might also point to another strategy for looking for non-Gaussian signals, in the sense that, again, because rare objects form from the non-Gaussian tails of distributions, we know that they should a priori have some information about the non-Gaussian nature of statistics. Okay, so I think my time is over, so I will just stop here and thank you for your attention.
Thank you very much, Vincent. It's a very nice talk. So I suppose now we're right on time to jump to the discussion session. So we've had a bunch of questions both during Marco and Vincent's talk. So I'll be calling them out in order. So the first question comes from Rajiv. If you want to go ahead and ask Marco your question, unmute yourself and please go ask.
Hello. Can you hear me?
Yes, yes. Hi.
Yeah. Hi, Marco. So I understand that you were trying to point out that you can produce the secondary gravitational waves from both the U1 and the SU2 gauge fields as a secondary background. Okay, and chirality seems to be one of the distinct imprints in these gravity waves. So I wanted to know whether there's any other distinct signature on these GWs which can be used to distinguish between the U1 and the SU2 gauge fields as the source.
Okay, this becomes a more complicated question. Let me just give you first one type of answer, and then I'll give you your answer. I'll just do share screen for 1 second. You see, I saw your question, so I was preparing this slide just to reply to your question. This was in the abelian case, where this was the plots I showed during the talk. But in principle, you have also non-Gaussianity in the gravitational waves. And of course, the question is how you see it experimentally. Here is in the CMB, how the non-Gaussianity would relate to BBB, the 3-point function. So here I'm showing L max that you reach in the experiment. And here I'm showing the signal to noise ratio. Sorry, the plot is not very large, but that's what I have. In the, you see, you need to have signal to noise ratio greater than 1. Solid lines are Planck-like experiment, and instead a dashed line would be cosmic variance limited experiment. On the right, if you violate parity, in principle, you could have even TB correlations, but you see, this is out of reach. You can also try to determine non-Gaussianity from interferometers. But there, you need to be careful what you try to determine. If you try to determine the 3-point function, HHH, this is something that is really not measurable, unfortunately, because of superposition of waves that arrive to your detectors is not going to be coherent. However, what you can try to measure is the 3-point function ρh, 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 which would be done in this CMB-like approach, as I was telling you. Now, related to your question, really, how you distinguish U1 from SU2, well, in SU2, you have more interactions, and these were computed, for example, by Komatsu and collaborators. So in principle, you have a different shape of non-Gaussianity. So these plots were done here for BBB, but in the equilateral case. But in principle, you may just need to go study the details of the shape to distinguish the additional interaction that you have in the SU2. Let me stress that I'm really not aware on SU2 model that would produce signal on CMB without being ruled out by other effects. So, but still one may find it, right? So I think one will need to enter in the details of the non-Gaussianity shape.
Subodh, can I just continue with the small follow-up question? Could there also be some non-trivial cross correlations here? Like
well, yeah. Between what and what?
Like your temperature and the B. Although they are very wide scales, but maybe there is something which is a very peculiar signature of these induced background in terms of a cross correlation.
Yeah. For example, on the bottom right, I'm really showing the effect of TB correlation. Unfortunately,
what I meant is the 3-point function, 3-point correlation.
I'm sorry. Yes, this also has been discussed in the literature. Yes, absolutely. Since you violate parity, you have all these extra things, and in principle, they are there. Now, the level, of course, depends on the model, and as I say, I have all my caveats that I already mentioned. But absolutely, these also are possible. Yes.
Yeah. Thanks a lot.
Thank you.
So maybe we'll actually just run through all the questions for Marco and then move to the questions from Vincent subsequently. There's quite a few for both. So Suratna, I believe you have a question for Marco if you want to unmute yourself and ask.
Yeah, so hi, there was interaction term for the warm quintessence model. So whether they have calculated the dissipation coefficient responsible for the interaction term, so that
yes.
Because a lot can be said by looking at the dissipation coefficient itself.
Let me just mention what has been done in relation to the U1 vector field. This is the slide I just prepared. So essentially, this will be, if you look on the left, the equation of motion for the inflaton with the back reaction term, and the Hubble equation with the back reaction term. And typically, the dominant term is the one in the equation of motion of the inflaton, because the inflaton has an equation of motion which is low-rho suppressed. So the first effect of the vector field will be in the equation of motion of the inflaton field. So these are completely generic, and here I'm using electromagnetic notation, even if I'm not assuming that the field is an electromagnetic one. So right, you have one field, you know, from when you have the gauge potential, how to compute the E field and the B field. Now, on the right is the calculation that is done by Amber and Sorbo if they assume constant psi, so constant value of phi dot. This will be the regime of the Amber-Sorbo solution. Then you can do approximation, you can understand what E dot B is, essentially that's the one that is really important. And then you can even find what value of psi you would assume. Now, and this value of psi is the one that on the plot you see as the dashed horizontal line. And the point I'm trying to make is that, at least from our studies, we don't really see a convergence to Amber-Sorbo solution, but we rather see these oscillations about it, essentially. So this is a difference between just solving the equation, starting from initial conditions which are not perfectly on the Amber-Sorbo line, or just to assume their approximation, I would say. So in a sense, for dissipation here, really what I mean these terms on the right-hand side of the equations of motion that can be computed once you know the gauge field abundance.
So Marco, you also have a question from Nicola. Nicola, if you want to unmute yourself and ask.
Oh yeah, no, hi. No, actually it was a question that I think it was already addressed. I was just suggesting that maybe also it could be interesting, I don't know if data has already been studied, but to look for a cross bispectra TTB, for example, for which, to be honest, you don't need necessarily to have parity violation, because you can play on the parity symmetries of B and T. So I don't know if that has been studied or analyzed, but maybe it could be something interesting to look at.
Yes,
it was just a comment.
Ciao, Nicola. I agree with you. When I was saying parity, I even realized that this was not applying to this specific bispectrum. No, I think it would be interesting to look at this more in detail, for sure. The question is, however, then my skepticism on what type of models will really produce it. But of course, you can study from the data analysis point of view. Sure.
And I was referring to the models you were describing, Marco. When you were showing the BBB bispectra, I was just asking.
Yeah, no, then I don't think this has been studied for the specific.
Okay, just okay.
I think there are studies for the SU2 model, which I'm more concerned about, but for this U1, I think it could be an interesting thing that maybe we can discuss in further.
Yes. Okay, sorry.
No, absolutely.
Okay. Thank you.
Thanks, Nicola.
So before we move on to questions to Vincent, I have a question for Marco. Maybe you can help me think through this, because I'm just puzzling through something, and I'd like your help to sort of help me understand how I might be thinking about this wrong, I think, which is the question of actually detecting chiral gravitational waves at an interferometer. So in the CMB, we're seeing a flash at a very particular moment, right? And so if you know, so for instance, with B mode polarization, if you have, you know, it doesn't matter if gravitational waves are coming from different directions. If there's a net overdensity, there's a net B mode polarization because it's a flash in one moment in time. Whereas for an interferometer, you're seeing gravitational waves come at all times, and you know, structures forming. And so will there really be a net chiral signal in an interferometer, or how can we disentangle?
Yes, yes, very good question. I also spent a lot of time picturing it in my mind when I did the first paper. Essentially, you do it statistically, right? Correlating interferometers. If you have only one chirality, there is a difference between a gravitational wave that always goes like this, or a gravitational wave that always goes like this. And so depending how you put the two interferometers, you can really get a statistical correlation even when you sum over signal from different directions. And this is technically computed in what people call the overlap functions between the two detectors. And here in the plot I'm showing, I mean, is just a technicality, but how these overlap functions are different from zero for the two different polarizations. But the intuitive approach is really to just think, right, how the when the gravity wave propagates, is the plane of squeezing that rotates. And so you can really tell the right from the left if you take correlations and you know the direction of arrival. And then you need to integrate overall sky. But once you do the angular integration, you have something that survives.
Okay. If you have a reference that maybe I could follow through on the details a bit more, you could put it in the chat box while we move on. But
well, it's this paper, Crowder et al. I'm one of the authors, so if it's the only paper. Mandik, Crowder, Peloso, and then there is an older paper by Seto that we reference to. But if you start from our paper, then you can look at the literature about it. Okay,
thank you very much.
Thank you.
So we'll now move on to questions for Vincent. You have quite a few, actually. So again, we'll go in order of them being asked. So Rajiv, maybe you want to ask your question to Vincent?
Yeah, hi again. So Vincent, hi. You made a remark in the beginning of your talk that it doesn't really matter what you choose the value of the critical overdensity, whether it is 0.8 or 1. But as you know that the PBH mass fraction is exponentially sensitive to delta C. So, and we know that a very slight change in the value of delta C does actually change the PBH mass fraction to a large extent. So can you clarify what do you mean by your remark? Thanks.
Yeah, sorry. So maybe what I said was a bit confusing. So first of all, first remark is if you form, so the dependence on delta C is usually like a Gaussian dependence, exponential minus 1 over delta C squared. Here it's only an exponential dependence because you have an exponential tail rather than a Gaussian tail. But still, it is true that if you change delta C by a small amount, you change by a big amount the number of the density of the black holes that you form. But what I was referring to is the fact that still you don't change the fact that you need to have a small mu. So if you wish, the dependence on mu is still much larger than the dependence on delta C. And therefore, even if you change a little bit delta C, so you will shift a little bit the curve that I've shown, but still the conclusion that mu should be less than 1 will remain true. That's what this is the only thing I meant.
Okay, so you meant that in your stochastic formalism, the change in delta C slightly will not really make any difference in the final.
What I meant is it doesn't change the conclusion that if mu is larger than 1, you overproduce primordial black holes. Now, if you want to work with a fine-tuned intermediate value of mu such that you don't overproduce, but at the same time you still have this interesting amount of primordial black holes, then of course at that point, then the value of delta C will become very important. This I completely agree. But I was just saying in terms of ruling out potentials on the basis of the overproduction problem, it doesn't really change.
Okay, yeah, thanks a lot.
Okay, our next question is from Swagat Mishra. And actually, I believe it's a question to both Vincent and Katie. Please go ahead and ask, Swagat.
Actually, I had two questions. The first one is a general question about your coarse graining scale. So I guess in length scale, it should be slightly higher than the Hubble scale. Right. But how to decide how high it is?
Yeah, that's a good question. So in principle, so this sigma parameter is that you refer to in the question in the chat box is indeed the scale, the parameter which sets at which scale exactly you coarse grain your theory. And ultimately, because this is the scale at which you incorporate back correction, it has to do with, and effectively at what scale do the fluctuations back react on the FLRW geometry. So, okay, in order to really answer that, you would need to better understand this. But on the other hand, a nice thing, at least in the thorough regime, is that at the end of the day, the result does not depend on sigma if you take it to be sufficiently small. So there is a limit when sigma is small, then the Langevin equation you obtain is sigma independent. In principle, in the amplitude of the noise, the h over 2 pi, you have some small sigma suppressed corrections. But you see, as soon as you take sigma to be sufficiently small, so if you coarse grain, I don't know, 10 times the Hubble radius or larger, then you don't see any sigma anymore, which is convenient because it means you don't have to to answer that question.
All right. Yes, yeah. And my second question was a little different. So when we study classically the initial conditions for inflation, we would usually put the classical equations and start. However, I guess especially for asymptotic flat potentials, if you go a little bit slightly 4, 5 phi in terms of Planck mass away from the CMB scale, I would guess you'll still get a lot of quantum diffusion there, right? So our classical conclusion that whether you have an attractor or not would be completely wrong, probably.
Right. So the first thing is you have to move away a lot from the CMB scales to get large stochastic correction. So if you think in terms of the the criterion that I shown, v prime squared less than v squared v double prime, if you take a plateau, let's say you take the Stravinsky potential, for instance. Of course, if you go very, very far on the plateau, then there is a point at which this criterion will be satisfied, and you will be dominated by quantum diffusion. But you need to move a very long way, right? Because the potential energy is fairly small compared to the Planck mass. But still, it is true that there is a regime where you're dominated by stochastic diffusion. And then in principle, if you really wanted to fully address the initial condition problem, you would also need to take into account the fact that the field is a quantum field. And I think so probably Katie can answer better than me, but I know that there are some works, there is a couple of papers by David Kaiser et al. Where they have a way to account for the fact that there are some small quantum fluctuations on small scales where they study initial conditions for inflation. But otherwise, it's I guess it's an open problem, right? Because you would have to solve completely quantum fields on curved backgrounds, but for arbitrary geometry, and yeah, I think it's still open.
Yeah. Thanks. So I'll just chip in and say, yeah, I think that's a good answer. I mean, it's really an open question. It isn't really something people have thought about. So I know the paper you mean by David Kaiser, and he does look at this kind of spectrum of quantum fluctuations. Yeah. But I think that they still treat them in a kind of classical way. So they're kind of evolving them with, the Klein-Gordon equation plus I think plus Newtonian gravity. But yeah, I mean, yeah, it's definitely a good point. Yeah.
Thank you.
Okay, if that answers your question, Swagat, we'll move on to Sharvari. Please unmute yourself and ask your question to Vincent.
Hi, my question is for Vasa as well as Katie, perhaps. So the universality in the PDF sort of signals some sort of an invariant in the dynamics. So I was wondering whether this is related to the robustness that Katie was talking about. So for a non-robust potential, you won't have these sort of attractors or invariants, and you won't see universality. So are the two connected?
I don't know. I mean, yeah, indeed. So the fact that you only have this specific combination of the height of the potential and the width of your quantum well, which appears through the nu squared combination, must mean something about some invariance somewhere. This I agree. However, I don't know how it is related to robustness in the sense of the initial condition problem. But
yeah, I'm not sure either. So I would say, I guess they could be related in some way. I mean, if you're talking about a very sort of flat part of the potential, then that tends to be something that's quite robust for starting inflation. But yeah, I'd have to think about it a bit more.
Yeah, thank you.
Before we take any more questions, I just want to check in very quickly with Sriram. We're supposed to take a little break now before.
We are fine. Just we can have one or two. I just see two more questions. You can allow them to ask.
Yeah. Okay. In which case, it may make sense. Should we still take a break afterwards, or move straight on to Robert's summary? We can decide.
We'll just take a 4-5 minutes break. Few minutes break.
Sounds good. Okay. So the next question is from Raghavendra. Please unmute yourself and ask.
Hello. This is to Professor Vincent. This is regarding the PDF arrived at, the non-Gaussian nature of the PDF that is arrived at using the delta in formalism.
Yeah.
There is the other source of non-Gaussianity that is typically calculated from the cubic order action of the scalar perturbations themselves. So is that non-Gaussianity taken into account, or how do these two kinds of non-Gaussianity compare against one another?
So you mean how the non-Gaussianity we get compares to the standard to Maldasena's consistency relation, for instance?
Exactly.
Yeah. So this is, it's a very good question. So in fact, one thing you can do is you take the full result of the stochastic delta n formalism, and then you have this parameter which tells you whether or not you're dominated by stochastic effect. Remember, there is this criterion. So you can define a ratio of the two sides of the criterion and say, well, when this ratio is small, you're dominated by classical drift. When it is large, you're dominated by stochastic effect. And then you can say, well, let's work in the near classical regime. So consider the case where this parameter is small and perform an expansion in this parameter. And analytically, you can show that if you do that, then you recover all the standard results. So the power spectrum at leading, so the mean number of field at leading order is just given by the classical formula, the classical solution of the Klein-Gordon equation. The power spectrum will give you the usual formula for the power spectrum. And then you can go one order beyond and compute FNL, and then you will get exactly Maldasena's consistency relation. Now, of course, if you perform the expansion one order beyond, you will get corrections to that. So you can compute the first correction to the power spectrum or the first correction to FNL, and you will get deviations. But at leading order, it is perfectly consistent. It gives the same thing.
Okay, so both of these are consistent, and this is model independent. As in,
yeah, this is model dependent. One thing I should say, however, is what we were able to show is the result for FNL, a local type of FNL. If you want to compute the bispectrum in any arbitrary configuration, then in principle you can, but in practice I don't know how to do that yet, because you have to, you have to resolve the full spatial structure of the field, and so correlations between the number of e-folds realized at different points and so on. And this, I mean, all the information is contained in the stochastic equation, but in practice, this has not been checked. But at least in the local configuration, this has been checked and it works. It gives exactly the same thing.
Okay, thank you. Thank you.
And we have time for one last question from Ashley. If you'd like to unmute yourself and please ask Vincent.
Hi, thanks. So as you quite rightly say, you need to have the sort of, you need to have a go beyond the slow roll approximation if you're going to have the sort of flat potential to produce the right sort of amount of primordial black holes you need, or rather to not overproduce them. But obviously when you go beyond slow roll, as you sort of hinting at earlier, your definition of sigma, i.e. like when modes properly classicalize, they classicalize a lot later during like an ultra slow roll period. So does this not affect like your dynamics in some sense, because suddenly you're delaying all the feeding into your sort of like average coarse grain quantity?
Yeah, that's right. So so what happens in the ultra roll case is somehow the role of the, so you see the reason why you have this quantum to classical transition in the sense that is usually discussed is because you have a growing mode and a decaying mode on super-Hubble scales. So if you wait long enough, the decaying mode has sufficiently decayed and can be neglected. And if you only have one mode, it means that you cannot build non-vanishing commutators and things like that if you have only one quantity, one phase space coordinate. And in this sense, things become classical. So in the case of ultra-slow roll, it is also true that you have a growing mode and the decaying mode, but the role of these two modes is flipped. So what used to be the growing mode of slow roll becomes the decaying mode, and vice versa. So what it means is, it is true that there is a phase, I mean, at the transition, soon after the transition between, say, slow roll and ultra slow roll, there is a phase where the two modes are of the same order, because you see one has decayed but starts to increase again, and then things become tricky. But then if you wait long enough, the decaying mode, the growing mode, which used to be the decaying mode, becomes much larger than the decaying mode, and still you also have this quantum to classical transition. And in that case, so if you wait to be deep in the ultra slow roll regime, then you're fine. Then you can still use the same sort of approach. The thing which makes technically the analysis more tricky is that now you have the phase space is two-dimensional, so not the one of perturbations, but the phase space of the field becomes two-dimensional because okay, Searle is an attractor. So if you know phi dot. So effectively, phase space is just one coordinate. In ultra-Searle, it's not the case anymore. If you know phi, you do not know phi dot. So you need to solve this two-dimensional problem. So it just means that instead of solving differential equations, you have partial differential equations. Ordinary differential equations, you have partial differential equations. And technically, it's a bit more difficult. But in principle, it's the same analysis can be done. If you wait to be deep in ultra-Searle.
Thanks, that makes sense.